A bad RAG score is not a diagnosis. Error analysis shows whether retrieval missed, distracted, or ranked the right evidence too low. You'll learn the shape of a workflow that audits retrieved answers against expected steps and surfaces retrieval error types. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Retrieval augmented generation is a pipeline problem, not just a single model problem. Folks reach for RAG when answers must be grounded in external text, docs, knowledge bases, support transcripts. When the generator stumbles, teams often point fingers at the model. But very often, the real problem lives upstream, the retriever or the ranking. Success is simply getting the right chunk near the top so the generator can do its job. At scale, a small slice of queries can create most of the pain. Figuring out whether queries never see the needed document, see it but too low in the ranks, or are drowned by convincing distractors tells you which fix to choose. The purpose of this video is to turn raw logs into a short diagnostic checklist you can act on. Think of this like triage. First, detect whether something is missing. Then split slow hits from outright misses. Then, find distractors that beat the truth by a risky margin. We'll show the pattern on a tiny example, then explain how the same signals extend to larger evaluation runs. We will build a compact audit that reads retrieval traces, compares them to ground truth, and emits 3 actionable signals per query so you can prioritize fixes. The code will be simple, readable, and focused on concepts, not on engineering scaffolding. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We start by logging where the first relevant chunk appears for each query. This snippet builds a toy retrieval log and surfaces first relevant ranks per query. Ever wonder whether a drop in recall means the right chunk never arrived or just showed up too late? We define CRELs as our ground truth query to document mapping, and retrieved as the scored rankings the retriever actually served. The loop walks those rankings, asking hits to store the earliest index where a relevant ID shows up, or none when the chunk never surfaced. That single pass already separates a pure miss from a slow hit before you tweak embeddings or re-rankers. The printed dictionary gives you query by query first hit positions, so you can instantly spot missing coverage and chunks buried too deep. Now, we need to tag each return chunk so we can measure how much noise the retriever is passing to the generator. This code labels each retrieved chunk as a hit or distractor and tracks their share. When your evaluation curves drop, do you know whether the retriever is stuffing the prompt with junk or simply missing the right chunk? We step through retrieved with enumerate, append a tuple of query doc rank score label into judged rows, and increment a simple counter whenever the label is distractor. Because we stash rank and score alongside the label, this table doubles as a breadcrumb trail for later drill downs or replays of the retrieval trace. Distractor share normalizes that noise to a per query rate so it stays comparable even if you change top K later. The printed ratios highlight which queries are drowning in distractors and which are most likely to derail the generator. Once we have per chunk labels, we turn positions into a metric so we can rank queries by severity. This example flags rank failures via reciprocal-rank traces. Is the retriever late or absent when the answer falls apart? We grow reciprocals by appending 1/rank for every query, letting none contribute 0, so misses pull the average down sharply. In parallel, rank alerts marks each query either as miss or with a human-readable threshold breach, like rank +3, which gives you a straightforward to-do list from the logs. Because the same structure stores MRR, Downstream notebooks can plot a metric without losing the categorical annotations. The printed alert map immediately separates the zero recall query from the lagging one, turning vague complaints into concrete leads. Now look at which wrong chunks are scoring above the truth and by how much. This snippet extracts the highest scoring distractors and their score gaps for each query. Which distractor chunk is stealing the spotlight from your relevant evidence? We reuse judged rows to iterate per query, letting best hits track the strongest true score while best bad captures the top scoring outsider. Gap report then stores both the distractor ID and its advantage, and high gaps filters for gaps above 0.2 to focus on genuinely dangerous cases. Because the computation reuses stored ranks and scores, it stays deterministic and cheap enough to run on every evaluation batch. The printed list shows which queries have distractors outranking the truth and quantifies the margin you need to close. Finally, combine these signals into a single, readable report, so your next fix is obvious. This code assembles a focused error report, so you know which failure class to fix first. Do you triage a missing document, a buried hit, or a distractor gap next? Misses compresses every query set difference into a short list, while rank failures reuses hits to capture only the ranks that break your acceptance threshold. We then look at gap report to pull the largest distractor advantage, surfacing both the query and the gap value, and carry MRR forward as the overall health signal. Report line stitches those signals into one deterministic string you can drop into logs or dashboards without post-processing. The printed summary spotlights the missed query, the slow query, and the worst gap, so your next fix is obvious. To map this tiny demo to real projects, run it over evaluation sets of hundreds or thousands of queries, and store the per query report in a table. You can attach timestamps and latency to see whether slow retrieval correlates with rank failures, and push the worst queries into a human review queue. The core signals survive scaling and point you straight to whether to add documents, tune the index, or retrain a re-ranker. Recap: this is a small diagnostic workflow that classifies retrieval errors into misses, rank problems, and distractor gaps. Use it when generators fail on grounded tasks or when recall drops for unclear reasons. One caveat: small toy thresholds do not generalize. Tune your rank threshold and gap cutoff for your dataset. Next step: tune top K and rerun this audit to see whether raising or lowering the candidate window moves queries out of the miss bucket or reduces the distractor share. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.